In this video, we're going to talk about what's called the Dirac Delta Function. The Dirac Delta Function. The word function is a bit of a misnomer. It's not really a function, but this is going to be some object, it's formally called a distribution, but this is going to be some object with the following properties. The first thing I want to do is to describe the unshifted delta function, and then we'll actually work with the shifted function, but they're very closely related. So what I want to do first is let's just talk about some properties here. Informally, I want to give you a way to think about this quote-unquote function informally, but informally delta of t is going to be infinity if t is equal to 0 and 0 otherwise. So this is going to be some function. We'll come back to the graph of this and why that's a reasonable intuition, but the function here is going to be as follows. It's going to have the following properties. So delta obeys the following properties. So the first is that if we integrate delta from negative infinity to infinity, we're going to get, I forgot my dt, we're going to get 1. Okay, that's a property of this delta distribution. The second property is that delta of t is going to be 0 if t is not equal to 0. So that's kind of, again, built in here. And the third property, and this is really the one that's going to be the most useful for us, is that if we integrate from negative infinity to infinity, delta of t times some other function, say g, what's going to happen is we're going to get whatever g is at this point 0. So it turns out we're going to get g of 0. That's how this function is defined. The way I like to think about this function is that if, just to lay down a little intuition here, if you were to have, let's say I were to have some function that's going to go from, say, negative epsilon to epsilon, and the height of this function is going to be, say, the height of this function is really going to be whatever we need in order for this area to be 1. So in our case, that means it's going to be 1 over 2 epsilon, because the distance from epsilon to negative epsilon is 2 epsilon. And so if I have 1 over 2 epsilon, that means that this is going to be some region that has area 1. So the rectangle there is going to have area 1 if you scale this appropriately. And what we're going to do is we're going to say, let's define this function f sub epsilon of t to be the function that's 1 over 2 epsilon if t is between negative epsilon and it's 0 otherwise. So this is our function that we've drawn. Really, if I wanted to draw this, if I wanted to be super careful about my drawing, let's get rid of the green. If I wanted to be super careful about my drawing, I should really draw it, just to be clear here, I should really draw it like this. And then we're looking at that. So the dotted lines are not part of the function, they're just to help us think about our drawing. And then we're still trying to find this area underneath here, right? That area being 1. So we're still trying to evaluate that integral, So what we're going to do is we're going to think about delta of t. So delta of t we're going to think of as the limit of f sub epsilon of t as epsilon goes to 0. And think about what's going to happen. If I take half the distance, right? So if I shorten, it doesn't matter what the scale is, but if I shorten the horizontal distance here, this height is going to be taller, right? Because we know that 1 over 2 epsilon goes to infinity as epsilon goes to 0. I should mention that this is just epsilon goes to 0 from the right. And so as epsilon gets smaller, the height of our rectangle is going to be larger. That's to make sure that this area of the rectangle is still going to be 1. And as epsilon goes to 0, this function's going to shoot off to infinity, and that's kind of where our intuition of delta of t comes from. Okay, so this is really that's not formally how it's defined, that's just good intuition. And so what's going to happen is that if you integrate any function against delta of t, so what I mean by against is if you take any function and multiply by delta of t and then integrate, what you're going to get is you end up with kind of this infinite amount of mass at a single point. And so you're going to get that function at that point, 0. Okay, so this is called the Dirac Delta Function. This is named after Paul Dirac, the famed physicist. And what we're going to do then is let's also talk about the shifted. So the shifted Dirac Delta Function. And this is going to be the same thing, except it just doesn't need to be symmetric about 0. It can be symmetric about any value. For our sake, for reasons that I'll make clear in a second, I'm going to assume that a here is positive, but a is going to be the amount that we shift by. And so we're going to define delta sub a of t to be delta of t minus a. So this delta with no subscript, like we were working with before, means that it's centered at 0. Delta sub a means that it's centered at a. And so this is going to be just 1 if t minus a is 0. In other words, if t is a, and 0 otherwise. I'm sorry, not 1. This is going to be infinity. You could think of this as infinity. This kind of is an informal definition. The first equality is the formal definition. Okay, so formally this is how it's defined. Once you have a delta, you can shift it that way. And so this is called the shifted delta function. And again, this has the same properties that this function is going to be 0. I'm not going to rewrite this, but replace all the zeros over here with a's, and you get the properties that we're talking about. So if you were to integrate delta sub a of t from negative infinity to infinity, you'll get 1. Delta sub a of t is going to be 0 if t is not equal to a. And finally, if you integrate, the one that I think is worth writing down is number 3. And this is one that we're going to use over and over. So we can call this 3b or call it whatever you want. But the property that we're going to use over and over is that if you integrate this function, delta sub a of t, times any other function, g, what's going to happen is you're going to get g at a. So this is going to be g of a. So that's the analog of the property. And this is a very important property that we're going to have for our delta function. Okay, so what we're going to do is talk about a few properties of the delta function. What we're going to do here is let's talk about the Laplace transform. So that's going to be the most obvious place to start here. So the Laplace transform of the delta function is going to be, just by definition, if we write it out, this is going to be the integral from 0 to infinity, e to the negative st, delta sub a of t dt. This, by the way, is this calculation is why I wanted a to be positive. If a is negative, what that would mean, so if a was negative, that would mean that what we're doing is we're integrating e to the negative st delta a of t. This is going to have, say, infinite mass at a, which is negative, but we're only integrating from 0 to infinity, and so this would still be 0, because we're not, you get to actually ignore this part if you're integrating from 0 to infinity. So because we're specifically going to apply these to differential equations and take the Laplace transform, we're going to always assume that a is positive. So that's always going to be a working assumption here. Now, if we integrate from 0 to infinity e to the negative st delta sub a of t, and if a is positive, for the reasons that we just said, this is actually the same as, you don't really need to write this out, but this is the same as the integral from negative infinity to infinity e to the negative st delta sub a of t dt. And the reason is that the integral from 0 to negative infinity is going to be 0. Again, for the same reasons that if a is positive, then the integral from from negative infinity to 0 is going to be 0. So you get to add that part for free if you want. Anyways, what we get here, using our property that I starred up above here, so let's put a little purple asterisk here. So this property tells us that what we're going to get is this other function that we're multiplying by delta at t equals a. And so that's going to be e to the negative as. And there's really no more calculation that we need to do here. Okay, so there's really no more calculation to do. We just That's the property. That's the Laplace transform. The Laplace transform, by the way, I should mention, also has one other property related to convolutions. It turns out that if you were to take any function g, and if you were to convolve g with delta sub a, what we're going to get is the integral from 0 to t. You get, let's do it this way. We're going to get delta sub a of y, g of t minus y, dy. And so let's just assume that a is between 0 and t, because otherwise this is going to be 0, and it's not a very interesting operation to convolve with a 0 function. But if a is going to be between 0 and t, let's think about what's going to happen. If we integrate this, we're going to end up with whatever this is at, so this is going to be g of, let's see, again we can do the usual thing where we write this as the integral from negative infinity to infinity, but we get g of t minus a. So convolving this with delta sub a is just really shifting this by a. And so therefore, if I were to take the unshifted delta function, what would happen? Well, we'd have, by the same calculation, we'd have the integral from 0 to t, delta t, g of t minus y. And what we're going to get is this function this function g at y equals 0, and you get g of t. So in other words, it turns out that delta is the identity, so this is the identity function or the identity element under the operation of convolution. Okay, so this delta Dirac function is the thing that you would convolve with the function to get itself. It plays the role of the identity. Okay, so that's a little bit about the delta function there.